All right, so now that we've kind of justified why we might want to take a deep dive into symmetry elements in a chemical context, now we're going to talk about what the different symmetry elements are. And so this general field that we're diving into is called group theory, named after point groups, which are groups of symmetry operations. And so when we're talking about molecules, there's just a few different symmetry elements that actually classes of symmetry elements that can exist. The first that we're going to go over is the rotation. So called proper rotation, rotational axes. This is just a normal rotation. It's given the nomenclature Cn, where you're doing a clockwise rotation is how it's defined by 360 degrees divided by n. So look at methane, for example. This has several different rotational, proper rotational axes in it. One of them is going right through where my cursor is going, this hydrogen-carbon bond. And so you can spin a methane molecule like that, and that's going to, if you spin it 120 degrees, that's going to take this hydrogen, put it into that hydrogen, this hydrogen that's in the front, put it in the back, and this hydrogen that's in the back, so spin around to the side here. So it's 120 degrees rotation because you have a tripod right on the bottom there. And so we would call this a C3 axis in this nomenclature. Water has a C2 axis, so you can see where that is, right through the oxygen, so that when you spin that 180 degrees, C2, 360 divided by 2 is 180, this hydrogen will go to this hydrogen will go to that hydrogen. So you're spinning the water molecule like that, right? This is ethylene or ethene. This also has a C2 axis. It actually has two C2 axes. And so if we want to look at what those are, one of them is going to be like this, right? To rotate it this way. So that's going to take this hydrogen to that hydrogen, this hydrogen to that hydrogen. Hydrogen's going to interchange. These carbons are going to interchange. So you're getting the same molecule back. That's what symmetry is all about. But it also has another C2 going this way. So that's rotating the molecule like this versus the other way was like this. Okay. And so that runs through the carbons. So just the hydrogens are going to interchange. Benzene, that has a C6 axis going right down into the molecule because it can rotate it 60 degrees, right? 360 divided by 6 is 60 degrees. So the highest order proper rotational axis is called the principal rotation axis. And we're always going to define this as the z-axis. This will just, it helps us have a common set of nomenclature for our future calculations that we're going to do. So what do I mean by highest order proper rotation? It means the one with the highest number n, okay? The C with the highest number n. So in cyclobutane, this is a C4. You can do C4 is 90 degrees, so that would take this carbon to that carbon, this carbon to that carbon, this hydrogen, that hydrogen, etc. But this molecule in the exact same spot also has a C2. You could do 180 degrees, take this carbon, flip it all the way to here, right? And this carbon would flip to there. So this molecule has some C2s and it has a C4, but because 4 is greater than 2, it's the highest one. We call this the principal rotation axis. And so we're going to define our z-axis to be in that direction. You can see there's also some C2s going this way, right? There's a C2 here, but that wouldn't be our principal axis because it's only C2. That would take this hydrogen, put it into here, this hydrogen, put it to here, and it would flip this one over here, etc. All right, so principal rotation axis, highest order one, we're always going to give it definition of z. How do you define x and y? Doesn't really matter. That you can choose however you want, and it turns out you'll get the same answer, or I shouldn't say you get the same answer. We'll get answers that are consistent with one another as long as all of us in the community uses z as the principal rotation axis. That's how the math turns out. All right, so that's rotation. First, proper rotation axis. That's the first type of symmetry element. Second type are inversion centers. And so inversion centers are given the symbol I. And the best way to think about an inversion center is to just know what the mathematical definition is. The mathematical definition is that every point x, y, z gets translated into negative x, negative y, negative z. So the way to think about this is that all the top points, the z points, will go to the bottom, right? Negative z. all the right points, maybe we call the right points x, will go to left points, negative x. All the points in front, maybe you call that y, will go to negative 1 into back. So something at the top left in the front will go to the bottom right and in the back, okay? And so a lot of molecules have inversion. So this platinum complex is one. You can see this is in the top left, sort of a little bit in the front, and it goes into the bottom right and sort of a little bit in the back, okay? And vice versa, this goes into here. The center is at the center, it stays at the center because the center is sort of like 0, 0, 0. So it went to negative 0, negative 0, negative 0. This point here, right? This point, we maybe say this is bottom left, and it ended up at top right, okay? Staggered ethane also has an inversion center. So this hydrogen, for example, it's in the back. It's in the slightly right side at the top of the molecule, and it's going to go to the front of the molecule, to the left, and well, I have top, so I lost track here. So top, right, and back, and this is bottom, left, and front, right? So it's always just going to be the opposite. I just lost track of which ones I said. So that's inversion center. Reflections are another type, and so there are horizontal reflections. We give all reflections the symbol sigma, Greek letter sigma. There are horizontal reflections. Those get sigma, the terminology sigma h. A horizontal reflection is a mirror plane that is perpendicular to the principal rotation axis of the molecule. So in benzene has a sigma h. The principal rotation axis is C6. That's the highest order rotation that there is. You can do 60-degree rotations. And perpendicular to that, there is a mirror plane, right? And so you can see this mirror plane, this benzene's a planar molecule, but if you think about it, the top half of this atom is going to go to the bottom half of this of the atom in the mirror plane, and vice versa. And so a general thing to look out for, anytime you have a planar molecule, completely planar, like this, like benzene, it's going to have a mirror plane in the plane, in the molecule plane, right? Don't forget that is a mirror plane. So this is a horizontal one, again, or perpendicular to the principal rotation axis. You can have ones that contain the principal rotation axis. And so those are called vertical reflections in one embodiment. I'll show you another one in a second, but sigma V's. Those contain the main principal rotation axis. So you can see this mirror plane takes this hydrogen, and where does it put it? It puts it to that hydrogen. Things in front of the mirror go to the equal point in the back of the mirror, and vice versa. There are also things called mirror planes called sigma Ds. The D stands for diagonal or dihedral. This is a mirror plane that also contains the main rotation axis of the molecule, but, okay, just like a sigma V, it contains the main rotation axis of the molecule, but it also bisects the angle created by two C2 axes perpendicular to it, okay? So when you have both sigma V and sigma D, the sigma D denotes the planes usually that do not pass through the atoms, but rather between them. So you can see here, the definition, the rigorous definition is that it bisects two perpendicular C2s. So the way you do this is you look at this and say, okay, first, principal rotation of axis of benzene, C6, good. I see that I have this mirror plane here, this mirror plane. I know that it contains the perpendicular, the principal rotation axis. So it's either going to be a sigma V or a sigma D. How do I know which one it is? Okay, let's first just look at this mirror plane a little bit. It's taking this atom and it's moving it to this atom, and it's taking this atom and moving it to this atom. Okay, so that's just getting on. It's taking that back hydrogen. That's just visualizing it a bit. How do I know if it's sigma V or sigma D? Well, you have to look for this perpendicular C2s. Okay. You have to look for two perpendicular C2s, perpendicular to the mirror plane. So here they are, spinning the molecule 180 degrees, okay? And there's two of them here, one going like that, right? And the other going with like that. And because this mirror plane is bisecting it, you can see it's right through there, comes out at 45 degree angle of these two near tens. That's how you know it's sigma d. Contrast that to the sigma v, right? The sigma v is actually in line with a C2. Okay, that's your C2 right there. So that's a difference, a little bit subtle, but it'll come up and it's good for us to know. Next, symmetry elements. So far we have sigma h's, sigma d's, sigma v's, 3 different types of mirror planes, and then we have the CMs, the principal rotation axis. There's another type of rotation, which is a little bit interesting. It's called the improper rotation axis. It's given the symbol SN. And this is a CN followed by a sigma H. It turns out that this is a unique symmetry operation. And some molecules, a lot of molecules will have this. Some molecules will only have this, amazingly, even if they don't have a C or sigma H by themselves. But the combination of both of them, they will have. So that's kind of interesting. That's a pretty rare case. I'll show you one in a later video. But just to visualize this, so if you're going to do a C4, an S4, you're going to do a C4 followed by sigma H. So you can write that as like CN multiplied by sigma H. That means followed by. Okay, so C4, so we're going to do an S4. So first we're going to do C4, so we're going to do a 90-degree rotation. What does that do? Well, that brought that A right here, right, kind of out in space here in front. That's where it is. Okay, and it brought the B in back, and the D and C now are kind of up and down. Okay, but then you're going to do a sigma H, so perpendicular mirror plane reflection to the C4. Right, C4 is here, so perpendicular to it, you're doing the C at sigma H. And so what does that do? That took D to the left side of the mirror plane, brought it to the right side of the mirror plane. So D is over here. And C went from the left side to the right side. And A went from the right side to the left side. And so look what happened. You ended up getting the same looking type of molecule where you have these green atoms in the same spots as when you started. So that molecule has an S4. So methane, tetrahedral molecules like methane have an S4. Staggered ethane actually has an S6. How does this work? It's a 60-degree rotation, okay? So it's a 60-degree rotation followed by a mirror plane. So let's track one atom, do a 60-degree rotation. Well, it's 120 degrees between this hydrogen and this hydrogen. So 60 degrees is going to be halfway through. So we're putting the atom there, but then we're reflecting it through this mirror plane. So it's going to come from the top, and then it's going to end up at the bottom right there. The last symmetry element is called identity. We give this the expression E. This is the symmetry of itself. This seems fairly pointless. Like, yeah, of course, everything has a symmetry of itself, and that's true. But it turns out to be very mathematically useful, and you'll see why later on. But yeah, this is giving E identity. Some molecules only have the identity operation. So here are some examples. Like if you have a carbon with 4 different substituents, that only has the identity operation. Or this molecule here, where you have 3 different substituents. All right, so that's it for symmetry operations and the different types of them. And now we'll be able to see what we can do with these symmetry operations once we know them.